Yeah. So, hello everyone. I will present the results of several studies of the Moran ore body in Kambalda in Western Australia. And I will start with the oldest sulfides in the system, then continue on with the main ore body, which you see here in this picture, and continue on with late ore stage sulfides. I will show you how the magmatic system evolves from the start to the end when it crystallizes, and we'll show you how the sulfides actually crystallize. But first, I'll tell you a little bit about komatiites because we haven't heard much today about that. Oh. All right. Komatiites are very low viscous ultramafic lava flows. They mostly occurred in the Archean, and the eruption temperature is thought to be above the liquidus temperature of the komatiites, which in this case would be about 600 degrees or even higher. And there are several occurrences in this lava flow system, what you see here, where sulfide deposits could occur. And the most important ones are here with the number 1, that are really thick, several hundred meters thick ultramafic cumulates, and sulfides are disseminated in these packages. And the second important ones are what you see here with these subparallel ground bounding folds, lava flows, channelized lava flows. And here within the channel, we form, or we have embayments where the sulfide sits actually at the base of the embayment of this lava flow. And I show you now a map of the Kambalda area that could look similar like that. You see in black here the known lava flows. And where the gaps are here, that is just because the contact of the base of the ultramafics are just too deep for exploration, so there's not much information known here. Whereas in this area in Kambalda, these lava flows partly crop out. I zoom in now into the Kambalda dome itself, and you see here the oldest rocks are the lamin basalt in yellow. And this lamin basalt, it's quite important, it's a hydrated basalt because it was flowing on the ocean floor. And then on top of that, you get just a few meters, maximum of 10 meters, of sulfide-rich chilled sediments. And they are thought to be the source of the sulfur for the ore bodies later on. In areas where these channels occurred, all these sediments have been thermally eroded, whereas in other areas, the sediments are still preserved and are followed by the Kambalda komatiite, which is between 200 and a little bit more and 1,000 meters in certain areas. This komatiite is composed of several lava flows, some only a few meters thick, some are up to 150 meters thick. But most of the ore bodies are actually occurring right on the base of the first lava flow. The komatiite then was followed by several more magmatic and sedimentary rocks, got intruded by phasic to intermediate magma, and got metamorphosed to upper green schist to lower amphibolite facies, and that's why Kambalda today forms this dome structure. Despite the metamorphism, there are a lot of igneous textures present in all sorts of different magmatic rocks here, and that's why we call it a basalt rather than a metabasalt or a green schist. The ore body that we will talk about today is shown down here, the Moran ore body. And on the next slide, I'll just show you a profile across the lava channel. You see here in white the spin effects of the basal flow, which is pretty much the crust of the lava flow against the cold ocean water. And here in the center, you see the thickness is about 90 meters. And that is a combination of flow inflation, but as well as thermomechanical erosion of the basal rocks. What you see here as well is that the main ore body is accompanied by satellite ore bodies on the western and the eastern flank. And the interesting bit is that the eastern flank, which is closer to the main ore body, is situated on basalt, whereas further away it is situated on sediments. And I show you now how this texture looks like right off from the contact. The sulfides actually melt sediments And because of the mixture of both melts, you form an emulsion. And you see here a map of this drill core, and you see actually that the silica part of this emulsion is bimodal in places. So we said having the sulfides melting the sediments here and then sulfides situated on basalt here, we actually think that this was an early concave embayment, and these flanking sulfides are just a relic of that. So this is a cartoon of it. Initially we have this concave embayment. The sulfides got entrained from the sediments next to it and just sit there as a melt pool. But once the sulfides are there, the thermal erosion actually accelerates, forming a steep-sided embayment and cooling and crystallizing the flanks of it. And that is the reason why we have sitting sulfides here on sediments, but here closer to the ore body already on the basalt. But why do we think that that the sulfides accelerate the thermal erosion? First is our ocean floor, the basalt was hydrated, so we got a lot of water in fractures or in zeolite minerals. And the other reason is the sulfide melt is quite heavy, really dense, but it's also very low viscous, similar to water, so it can easily penetrate into these fractures. And the temperature difference of, let's say, 1600 degrees to, let's say, 4 degrees means that immediately the water is flash boiling, creating its own network of microfractures around the larger fractures. And that is why the sulfides can even further penetrate into this rock. Once certain basalt class spend a little bit of time in this hot sulfide melt, they start melting themselves and forming melt films around class or on the sulfide basalt contact. And you see here an example of that. Once this basalt melt film becomes too thick, it becomes unstable and forms this sulfide melt plumes rising up. And this is a drill core photo of one of these melt plumes, and they actually occur everywhere where the sulfide melt is situated on the basalt. So on the western part of this flank, and here all over the contact of the ore body with the basalt underneath. And there are a lot of works, publications in the past that say that most of these pinch outs are actually tectonic. But this texture is one reason why we think it's actually a magmatic pinch out. And here you see in gray where this pinch out, so where the sulfides melt sideways, is completely surrounding the ore body, which wouldn't happen in tectonic environment. Another reason are these textures, and I will show you now a photo of one of the pinch outs up here. This is an enlargement of this area here. You see the base is just full of these basalt melt plumes. There's a little tectonism going on, of course, because there's a stark rheological contrast. But you see here in this drill hole, just a couple of meters away, an undisturbed contact where you have skeletal amphibole and skeletal chromite crystals growing in the sulfide melt, just underneath an emulsion layer, a basalt and sulfide emulsion layer. And on top, we find a layer with a lot of amygdales in the basalt. And the London basalt usually doesn't have any amygdales at all. So we think all the melt, the basalt melt that is produced there floats through the massive sulfides, and it's trapped in certain areas where the pinch out is a little bit higher and forming a silicate melt layer on top of the sulfides. And the amygdales represent pretty much the hydrated nature of the basalt. How does that happen? In the steep-sided embayment, we got a little bit of a sulfide melt sitting there, which is more dense than the basalt. And we got a high height of komatiite lava, which is a little bit less dense than the basalt. So overall, the pressures between the embayment and next to the embayment are pretty equal. But once the lava flow system starts to cool down, it forms olivine, and the olivine actually sinks into the sulfide melt, forming this matrix or net texture ore. And that is called this billiard ball model, which actually was developed by Tony Nordred. With that sudden increase in the sulfide melt depth, the pressure here in the embayment strongly increases and is now much higher than next to the embayment, forcing the sulfide melt to melt sideways. And that's how we create the pinch outs. But talking about net texture or matrix ore, what are they doing in the ore body? This is another profile where you can see the difference between net texture and massive sulfides. And you see that in the center of the ore body, the massive sulfides are thinnest, only about 20-30 centimeters, whereas in the flank, in the pinch outs, they reach up to 4 to 5 meters. And the net texture, you see completely the opposite. They are only found in these open contact positions where it's overlain by komatiite and not in the pinch outs. And they're thickest in the center of the ore body. This is a photo here. You see here the basalt, you see the massive sulfides, and then you see something what is untypical for Kambalda. You have one layer of net textured sulfides, then you have a barren layer, and you have another net textured layer. And in the next couple of slides, I will explain you what we think happened there. First, I will show you a map of only the net textured layer 1, how the distribution of that is over the ore body. You see here the map. That is the proportion of net textured layer 1 compared to the overall sulfides, of massive sulfides compared to net textured layer 1. And you see next to the pinch outs, how you would expect it, it's the lowest amount. And then here in the center, that is where net textured layer 1 is thickest. But then you see a gap here towards the north. And we can explain that if we look through along a profile, how the lava is flowing over the embayment. When it enters the embayment, you start to form eddies. So the settling olivine can't actually settle in this area and get transported more towards the south. And that explains the higher proportion of net textured sulfides here compared to there. Then it will continue to settle and continue to cool down. So at some stage, we will crystallize interstitial silicate melt in between here, and that prevents further net texture layer 1 formation. And continuous cooling will mean that we have a crystal mush coming down. And at some stage, this crystal mush brought down sulfide droplets, probably from the ore body further up. So we have
2 minutes, Sebastian.
Yep. So we have a co-settling of olivine crystals and sulfides, explaining the second layer. Quickly going into the geochemistry to see the crystallization of the sulfides. In the left image, you see elements that remain in the sulfide melt. Here you see elements that partition into MSS. And it appears that the crystallization started from the pinch out, where you have the highest proportion of these elements here, and in the central area here you have the highest concentration of elements that stay in the melt. So we think because of the pinch out geometry, it cools from the side towards the center of the ore body. I will skip that. I show you now another profile where we have the chemistry through the massive sulfides into the net textured layer. And there is something what is typically found in Kambalda and in some Canadian deposits, that the massive sulfides, represented by the circle here, have apparently less fractionated sulfides than the net textured layer above. And how can we explain that? We form our net textured layer, and at some stage the liquidus temperature of sulfides is reached, and we start to form MSS. And the MSS in this case is crystallizing sideways, otherwise we wouldn't get this geometry. And the idea is that it pushes a boundary layer of incompatible elements in front of this crystallization front. And that works because of the low viscosity and the very fast chemical diffusion because of that. The crystallization front reaches at the end the center of the ore body, which is represented here by yellow. And with graphical analysis, we calculated the amount of that, and that's less of 1% of the initial sulfide content. So we have here the very last fractionated melt. And that explains as well here why we have higher fractionated sulfides sitting in the net texture compared of the massive sulfides, because they are representing an MSS cumulant. And in the central part, we find a very high amount of interplanetary elements, and they typically form this dihedral arsenides surrounded by unhedral tellurides, and together with a sudden drop in this area here of the cobalt content in pentlandite, we think that there's an immiscible arsenide telluride melt forming right at the end. Okay, thank you very much.